Welcome to session for Computational Algebra. I am Siddhi Ambore from IIT Gandhinagar, and today we will discuss problems related to syllabus from week 2. That is problems related to initial ideal, division algorithm, Gröbner basis, solving polynomial equations, and Nullstellensatz. Okay, so we will start with our first question of today. Question 1. Let K be a field and R is equal to K x1 to xn. Then give R. So R is this polynomial ring in x1, x2, x3. Then these three variables, and give R the graded reverse lexicographic monomial order. So we know what this order is. I will still recall this order. And let it F. So F is this polynomial from this ring x1 cube plus x2 square x3 square plus x3 cube plus x2 x3 square x2 x3 cube. Okay, then the initial term of f minus in f. So this f is our polynomial which is given here, and in f, so this is something called as leading term or initial term of a polynomial. And now when so this term is actually a monomial, and then f minus that term again gives me a polynomial. So they are asking us to give an initial term of this new polynomial f minus initial term of f. And they give this example, whether it is x1 cube, second one is x2 cube, x3 cube, and third one is x3 square, and fourth one is x2 x3 cube. Okay, and let me just recall the definitions of what is initial term. So in order to define initial term, let us first define what is term. So let f belongs to r minus 0. So r is some commutative ring with the multiplication identity and with some order, and to define we do not actually need order. So let r be any ring and f be any element, non-zero element of the ring. A term of f is a monomial. R is, let me just write here, polynomial ring. Monomial of R that appears in F with a zero quotient from K. When I say this, it means that my R is some polynomial ring with coefficients from field K. Let me write field, or K could be a ring also. In our case, it's commutative ring. When I say commutative ring, again it is with multiplication identity, multiplicative identity or unity. Okay, so this is the definition of term. So term is just something or polynomial. So for example, in this F, terms this x1 cube is a term, x2 square, x3 square is a term, x3 cube is a term, and each this monomial gives us a term of polynomial. Okay, and for this from these terms, if f is in R and again f is non-zero in R, the initial term of f is the largest term of f. So when I say largest, we already are considering this polynomial ring with order. When I say order, I mean monomial order. With monomial order, greater symbol. Okay, so term with respect to the given monomial order. And it is denoted by this in f, which is already used in the question. So this is the initial term. So now we have these four terms in this f. So we have to find out which is the largest among these terms, and we have given the order of this polynomial ring R is graded reverse lexicographic. So quickly, for graded reverse lexicography, a monomial of this form is greater than this monomial. x1 power ai, x1 power a, xn power an is greater than, let me write G Gravely. If summation ai is greater than summation a, that is degree of the first monomial is greater than degree of second monomial, and second is that summation ai is equal to summation bi. And when we have this summation be equal, then we want ai minus bi negative the largest I with ai not equal to bi. Okay, so note that here we are working with the graded reverse lexicographic. So it works with the degrees. So definitely degree of these two terms, so let me color them. Degree of these terms is definitely smaller than degree of these two terms. Okay, so this one shaded with this bluish color is even smaller than the terms which are highlighted with yellow. So we just have to check to find the initial term of f. We just have to compare that which one of this is bigger with respect to graded reverse lexicographic order. Is it understandable? Please, if you have any, please write it in the chat or unmute yourself and ask. Okay, so we just have to compare since degree the first and third term has degree 3 and rest second and fourth term has degree 4. We just have to find the initial term of f, we have to compare only second and fourth term. Let us compare x2 square, 3 square, and here x2, x3 cube, right? And here, so the 0, 2, 2, and here I have 0, 1, 3. And when I subtract, the last term is 0, 1, minus 1. So since the highest I for which ai minus bi is negative, so we have this greater than this with graded reverse lexicographic order, reverse lexicographic order. Okay. So therefore, initial term of f is x2 square, x3 square. And when I subtract f minus this in f, what I will get is this x1 cube, third, this is second term, so which we are subtracting. Okay, so this was second term. So rest x minus or plus. So everything is plus x3 cube plus x2, x3 square. Oh, x2, x3 cube. Okay, and here again, these are degree 3 terms. Degree is equal to 3, and here degree is 4. So therefore, initial term of this f minus in f is this x2, x3 cube. Is this okay? Okay. Sorry for the background noise if you can hear it. We're with the second question now. If you have any doubt, please let me know. Otherwise, we will start with the second question. True or false. So we have to check whether the statement is true or false. In K, X1 is with like order. The set X1 minus X3 square, X1, X2 minus X3 cube is a Gröbner basis for the ideal generated by. Okay. So we have to check whether ideal generated by the. So we have to check whether these two terms forms a Gröbner basis or not. So let us define what is Gröbner basis. So let I be an R ideal. Okay, so I be an R ideal means I is an ideal in R, and a subset. I hope I'm clearly audible. Please let me know if that is not the case. Is a Gröbner basis of I with respect to this order if this mod of G is less than. So G is a finite in R, and we have this, that initial terms of F such that F in I. So this initial ideal of I is actually ideal generated by these initial terms of F. And what this is set of all such that F belongs to I. Is this okay? The definition of Gröbner basis. So it is a set for which the initial terms of elements from G generates the entire set of entire initial ideal. Okay. I hope that is okay. Is there any problem in the definition? I mean, if there is doubt, please let me know. If
hello, ma'am.
yes.
In the first question, the
Okay.
reverse graded reverse lexicographic order. So
Okay.
if order is if total order is same, then we are preferring the
So
the exponent of the largest the x3 part.
yes.
So x3
Yes.
cube should be x3 cube should be preferable to x3 square. So I think in graded reverse lexicographic order, x2 x3 cube should be greater than x2 square x3 cube square, right?
Okay, so let us try to calculate this in Macaulay too. Okay, let us try that and let us see what it gives me. Okay, so
Means like what I want
yes.
Usually the way we think is first we will compare the total order. If total order is same, the lexicographer will prefer the x1 first. That is, if
Yes,
x1
exactly.
power is more, we'll prefer that first.
Yes, exactly.
In reverse, the x3 power will prefer first. So in this x2 x3 cube, so 3 x3 has exponent 3, so it should be right. Yeah. Please try to please explain.
Is clear, right? To you? The
Sorry, ma'am.
definition. is this. So the definition is this. So when we have summation equal, the largest possible where AI minus BI is negative.
Yes. If can you
Yes.
make some comments on like AI minus BI less than 0? What it means?
So it means that when I do this, when I take this, really sorry for the background. When I have this vector, the largest index, we check where it is non-zero. And if that largest, it at that largest index, when AI minus BI is negative, then this monomial with exponents from AI is greater than monomials from monomial with exponents BI.
So in reverse lexicographic order, we are preferring x2 powers ahead of x3, right? Because
Yes,
it
X2
should be
also,
other way around. So there is a confusion. Even in
reverse lexicographic, just a second, even in reverse lexicographic, this is the case. Even in reverse lexicographic, this is the case. Okay, because see, when I do this x1 is what? 1, 0. Just take, we are comparing 2, and x2 is what? 0, 1. When I compare them, it is 1, minus 1. And as per the definition, AI minus BI is less than 0 for the highest, largest index. So this term, so x1 is anyway greater than xn. So we are not here just looking at whether the largest, I mean, you are saying the variable with the highest subscript must be given more weight. Just like in lexicographic order, the least one is given more weight, kind of thing, right?
Yes, ma'am. There is a confusion. Can you clarify?
Okay.
In definition,
the definition of reverse lexicography, graded reverse lexicography. Okay.
Yeah. Or
so
by
just
Macaulay, can we check? Yeah.
So you want me to try it in the Macaulay too?
No, if you're sure, then you please say that.
No. We
I'm
can do
just
it.
trying
And
to understand. I don't. Means like in writing, this is the way, the definition. But to think, when I have two monomials, so I don't have to,
Yes. I mean,
so
like when
what
we
is
look
the
at,
way?
Can you
I
describe in
normal
normal
language?
Yes. I mean, it is not as easy to realize as lexicographic order. That's what you are trying to say.
Yeah, means like first I'll compare the total order. If like if total order is same, only those terms I'll compare first. Now, should I go for like x2? If x2 has more power, then I'll take that. I'll prefer that term in graded reverse lexicographic. That is what you're saying, right? But I feel like x3, if x3 has more power, then it is reverse. Otherwise, it is lexicography. If what we concluded is x2 square x3 cube x3 square is preferable. I mean, in this.
Okay.
Okay. I'll
see when we have this monomial, just let me show you. It has nothing to do with what is the power of x1 and x2. For example, if you're saying that we are preferring x2 and so let me just show you that this term, this x2 x3 cube, or this, let me take x2 square x3 cube is anyway less than x1 cube x3 square, sorry, x1 square x3 square. What I was writing, yeah, here it must be square. I got confused. So the thing is, the last term, you just have to look at the last degree. Don't look at it like the way we did for lexicographic order. Try to look at it as the largest term where ai minus bi is less than 0 becomes our highest term. Okay, and let me just show you how to define this leading Macaulay 2. Let me just share my screen. Can you all see this screen? Macaulay 2 screen? Hello? Yes, okay. So let me just, so we are working with graded reverse lexicographic. Okay. So there are 3 variable ring with the monomial order. So this is the code for graded reverse lexicographic. Okay. Server is having some errors. Okay. And again, now I'm defining this monomial. X1 cube plus x2 square star x3 square plus x3 cube plus x2 star x3 cube, right? So this is my polynomial, and when I want to find the lead term, so in Macaulay 2, instead of initial, they use something called as lead term as a, what I can say, function name for finding initial term. So when I write this, it gives me this. Oh, okay, I set with the degrees. It is square here, and now it is correct. And now lead term of f is this. So this was our polynomial, and this is the leading term. So as you can say, even though this second term has highest power of 3. Okay, so in lexicographic order, higher the power of x1, bigger the monomial is. However, in reverse lexicographic order, power of highest index term greater the monomial. So the last variable, so in this case, when the x3 has least power, it becomes the highest.
Okay. Thank you. This is what I want. Yeah, thank you.
Yeah. So when we take in lexicographic order, when the same degree is there and the least indexed variable has highest power, it becomes largest. But in case of graded reverse lexicography, the highest indexed variable has least element, it becomes the largest. That's what happened in this case also. And that's when we will get ai minus I to be negative, when the degree of this bi term is least. Okay. And similarly, so we wanted to find this lead now of, see that this T of lead term is capital, and this F minus now lead term is F. So it already understand what this is, lead term of F minus lead term of F. Okay. So, and let us see what it is. It is x2, x3 cube. This is what we also got. Okay. I hope this helps. Is it okay?
Yes, ma'am. Thank you.
Okay, sure. And okay, so that's, let me check. Okay, and similarly, if you want to find the initial ideal, we will use it in our next question, and which I already wrote. It was something related to initial ideal. Okay, so I define some ideal. Let me just randomly define some ideal. we do not have 4, right? We define ring with 3 variables. 2 and okay, and of I. Okay, now this I in ideal, and when we do this, it gives me an ideal. Okay, it gives me an ideal which is generated by all the initial terms of elements from this ideal I. Is it okay? This is how we can also find the initial ideal of our ideal I. And the lead term of polynomial gives me the initial term, and when I do lead term of ideal, it gives me the initial ideal of that ideal I. Is it okay? Okay, so go back to the question again. Let me share the screen. Okay, so I hope the now definition of graded reverse lexicographic order is clear. And now we will move to the second question. So second question was asking about the true and false, and we have to check whether this set forms a Gröbner basis of ideal generated by these two elements. Okay, and let's check whether that is the case. And sorry, they are saying that if this set x1 minus x3 square, comma x1 x2 minus x3 cube is Gröbner basis. So let me write shorthand Gröbner GB for Gröbner basis of I. Then we have that initial ideal. The initial ideal of I must be equal to what? Initial term of these two. So now we are in lexicographic order. It is not even graded reverse lexicographic order. It is lexicographic order. So the moment something with x1 gets the highest, becomes the largest among the polynomials. So we have x1 here. So x1, and here among x1, x2, and x3 is 2. So among these two terms, we have x1, x2 as the largest term. Okay, or the initial term of this second polynomial. So in that case, so when I have this ideal generated by x1 and x1, x2, it is clearly only the ideal generated by x1, right? Is there any doubt here? Because note that this x1, x2 belongs to ideal generated by x1. You can get rid of this term. I did not want to use this, but we can get rid of this term if that helps. Okay, because since x1, x2 is already in that ideal generated by x1. So we have to check whether this is this is true or not, that whether initial ideal of I must be this. Okay, but now check this polynomial x2 into x1 minus x3 square. So we are multiplying this and subtracting with x1, x2 minus x3 cube. Okay, so because this here we have x1, x2, and what we get here is x1, x2 minus x2, x3 square minus x1, x2 plus x3 cube. Is it okay? And now when I subtract this, I get this polynomial x2, x3 square plus x3 cube. Now what is now this element? So let me call this element P. So this element, or why did you do in this step? Okay, so my aim was, so we have these two elements. Okay, the actual thing which I did was, I have these two terms. Okay, with the x1 and in x1, x2, this x1 is smallest and x1, x2 is largest. So when I saw this question, my first aim was to do this. Divide this polynomial with x1, x2 minus x3 cube. Okay. And I will get, when I multiply this element by x2, this is polynomial division. Okay. And then x1, x2 minus x2, x3 cube. So when you have such elements, polynomials, where the degree of one of them is smaller than degree of other, and one of the or of the term divisible by, then try polynomial division. Okay. And whatever reminder you get here, it reminder to be, I think it should be minus, both are minus, right? Okay. So here I get x2, x3 square minus x3 cube. Okay. And clearly this element, this belongs to my ideal I, right? Because what this is, just subtracting this multiplication of these two from this, and this element belongs to I. Okay, so when so you will learn something as S polynomial in upcoming lecture, where you will learn how we can check whether given polynomial form Gröbner basis or not. Okay, that is not yet covered in the given lectures, but that's how we do it. So we try to subtract, and this element is there in ideal I. Okay, and that's what I wrote here actually. Okay, with the subtraction going the other way around, or I can just do this minus and this plus, and this plus this minus. That doesn't matter actually. Okay, because anyway we are working over a field, so we have -1 in there, so minus doesn't play much role here. But in now we have this element which is now part of my ideal I, with what is the initial term of this. So they these are two terms with degree 3, and we are in lexicographic order. So anyway we have x2, so this x2 x3 square is greater than x3 cube, and this implies this initial of this polynomial x3 square minus x3 cube is actually x2 x3 square, but this monomial x2 x3 square doesn't belong to this ideal generated by x1, right? Is this clear?
Yeah, clear.
Okay. So my aim was, since x1 I have here and here also I have x1, I tried to get rid of this term and obtain some polynomial which has initial term different from which does not have any multiple of x1. That was my aim here actually. And this does not belong to ideal generated by x1. Therefore, this, so it fails the second condition of Gröbner basis, that one, that initial ideal must form. This is the definition. Okay, so that's why this G, or this set we had, let me give this set G, is not a Gröbner basis of this ideal I. Is it okay?
Yeah. What is the name of the polynomial that you said, which has not been covered yet? You said something, right?
Yes, which is not in I.
No. You said that some polynomial is
S
there.
polynomial. S polynomial.
Oh,
S
okay.
polynomial, S polynomial, yes, S polynomial. It is denoted by something like this, and where this F and G are elements from my set G, which I'm trying to check whether it's Gröbner basis or not.
Okay.
Okay. It is there. Yes.
If we have three elements in our set, F,
Mhm.
G, and H, then how to
So,
decide that which polynomial to divide with, like, the you choose
Okay.
x1 minus x3 cube.
Okay.
So the initial term, by that way, we choose whom to decide, whom to divide.
So whenever we try to divide, we arrange the polynomial in highest degree to lowest degree form. So it is like decreasing terms we arrange and see whether any of the initial term is divisible by other or not. So for example, here this initial term was, this initial term, like this first initial term divides the second one. So I can clearly get rid of this, let me just use some. So I can get rid of this monomial using this first one, right? This term I can get rid of using by multiplying this term by x2 and subtracting. So it is just kind of guesswork and trial and error. Since I already tried it, I just showed it to you. But yeah, you just have to get rid of the terms which you don't want, kind of, or which are already initial terms. So when you get rid of this x1 and this x1, x2, definitely whatever you are left with is something which does not have x1 in it. I mean, it's not always the case, but since these are only two-term polynomials or binomial, that's happening here.
So,
Here,
everything is dependable on the order.
yes,
If
order
we change the
as
order,
well
it
as
is possible that it is not a Gröbner basis, but with respect to collects, reverse legs, it might be.
yes,
Possible.
definitely.
Okay.
Yeah, definitely. In fact, that's also the case. Like some sets are Gröbner basis with respect to one order, but they need not be Gröbner basis with respect to another order.
Okay.
That is also very well possible. So, and in this case, why I tried to get rid of x1, x2 is because when I saw that this ideal generated by this in G, this ideal, which correspond to this ideal here, is actually generated by x1. So my plan was to eliminate, try to obtain a polynomial which does not have any x1 term. Because we are working in lexicographic order, and already as I guess Rashid pointed out that x1 has like highest weightage when we work with lexicographic order. So that was the plan to obtain this counter example. Is that okay?
Yes.
Okay. So that's it for now. So we'll move to this next turn, and
So by this method, we know this is not a Gröbner basis for ideal generated by A, but we don't know whether it is, if something is Gröbner basis or not. Like we can contradict it by now. With this method, we can find some contradiction whether it is. It should satisfy this initial ideal should be generated by its initial terms.
yes.
So it is not satisfying, but we don't have any method right now to conclude that whether it is Gröbner basis for this ideal generated by A.
So for now, we got a counter example where a monomial. So we wanted to check this inequality, this equality, right? That whether this initial ideal is actually generated by this initial terms of these elements from G, right? We wanted to check this, and here actually this is initial ideal, and sorry, it is not. It is actually set of. It is actually set of all initial terms of f, and it is also ideal generated by set of all initial terms of f, where f is any given polynomial in I, and any given polynomial I is all the all the polynomial combinations of the generators. So these two sets are
what
different.
I want to ask, like, given in any set of monomials or
Yes.
polynomials, how to ensure that that is a Gröbner basis for the ideal generated by it? by that
Yes,
side?
yes. So there is something called as Book-Burger algorithm, which you will learn up in next week's syllabus, and so it is called as Book-Burger algorithm. So it gives us a Gröbner basis from the given generating set of ideal I. So there is algorithm to actually obtain a Book-Burger algorithm. So by that algorithm, we have to add this element as well in the Gröbner basis. Okay, so that's not yet covered, but yeah, is it like understandable? So what we do is, whatever generating set we have, we keep on adding ideal elements to it till we get this equality. And this equality holds. I mean, this process is stoppable or stops somewhere or finite using the fact that we are working in a polynomial ring, which is a Noetherian, and every ideal is finitely generated there. And our monomial ideal in I is also ideal in that ring. This polynomial which is Noetherian, and it is finitely generated. Does that make sense? I mean, it requires a few terminologies to understand, but let me just show you this, which we calculated earlier, which we have already calculated. Let me share this screen. See here, can you see this screen, Macaulay 2? Here my idea was generated by three terms, only these three terms, x1 into x3 minus x2 cube, x1 into x3 power 4, and this term, x1 power 7 and x2. So this is ideal I was generated by these three elements. But when I try to find this initial ideal, it is generated by these four elements. So definitely initial terms of these three elements cannot be equal to the ideal generated by four elements, right? I mean, do you understand what I'm trying to say here? And when you want to find the Gröbner basis of this ideal I, let us see, James. So this is the code for finding small I, the Gröbner basis. So Gröbner basis contain these four terms. See, we have one extra term. So this was our first term, x1, x2, x3 cube. We have this x1, x3 power 4. We have this last term. Along with that, we have this extra term. Can you see this? I mean, we have to add elements to our generating set in order to get the Gröbner basis. Does that make sense? I mean, for now. So for your question, the answer is yes, we have algorithm to find a Gröbner basis. Also check whether given set is Gröbner basis or not. And you can manually do that actually. But Macaulay 2 already has those algorithms. And we can just check whether the given set is Gröbner basis or not. So this is Gröbner basis with respect to graded reverse lexicographic order. But this need not be again a Gröbner basis with respect to some other order. So let us check. Let us work with the same ideal and check whether it gives me the same Gröbner basis with respect to some other order, other order or not. So let me define. So earlier order was graded reverse lexicographic. So let me take this x1 to x3, right? And my monomial will be lexicographic order. Okay, and my I is again the same I. Okay, and now let me check this James GBI. And see, now the Gröbner basis has 10 elements. Are you, I mean, getting what I'm trying to say here? It completely depends on the order and what are the generators you are choosing. Okay, so for with respect to graded reverse lexicographic order, we only needed 4 polynomials to form a Gröbner basis. But with respect to lexicographic order, we needed 10 terms to obtain a Gröbner basis. So it is like, okay, so it's like when you do that Book-Burger algorithm, it is based on that finding S polynomial and doing division of a polynomials, and whatever remainder we get, we check more or less I'm just explaining, we check the initial term of that remainder, and if it's there, okay, if it is not, we add that term to our polynomial in our set, which is we are trying to make a Gröbner basis.
So,
Yeah.
the number of elements in the Gröbner basis,
Yes.
does it depend only on the order, or like, means is it unique for any ideal? Means that number can be associate that number to this ideal, some kind of dimension or something like that. Means is that number the cardinality of Gröbner basis for an ideal? Is it unique?
Okay, so you are saying the cardinality
for,
of Gröbner basis, whether it is unique?
Yeah, O12, is it 10 is unique number associated to the ideal I? The 10. You know,
Okay.
the 10 number. Or because we fixed order, like graded lex. So with respect to that, that number 10 is unique to that ideal, or like does it depend on any other thing?
I don't think so, because given ideal could have multiple, what I can say,
So like a vector space, like number bases may be different, but like number of bases, that cardinality should be the same.
No. That's not.
It's
That's
not like
not
that.
the
Okay.
case. No, it's not like that. We will see one example at the end where how Macaulay gives us two different Gröbner bases and so on. Okay, and I mean not two different Gröbner bases, but it works differently. When we try to find Gröbner basis, it actually depends on how you are writing or which elements you are choosing. Because for example, if you try to find take your Z and try to generate Z, we can take generator to be only 1 or 2 and 3, if you know. And in that case, both works fine. So if I had chosen some different generators of this ideal I, which is very, very possible, we can have different Gröbner bases.
Okay, so Gröbner basis is not unique for any ideal.
So it actually depends on from which generating set we are starting. If you follow the Book-Burger algorithm, it depends on which generating set you are starting with. And there is something also called as reduced Gröbner basis, and which more or less is unique. Okay, so in general, Gröbner basis is not unique, but reduced Gröbner basis has some unique properties.
Okay, so for any ideal, there is a unique Gröbner basis, some kind of
Yes,
reduced.
we can associate.
So that number is constant for that ideal. So that number we can use to identify that ideal. Means we can associate that number to that ideal. Something.
Yes, we can.
Okay.
If you want, or if there is some significance of that number, then definitely we must associate.
So it's well defined. Okay.
Yes. It will be finite. Okay, reduced Gröbner basis has same cardinality as far as I'm not sure at this moment, but yeah, reduced Gröbner basis has unique cardinality. Doesn't matter from where you start, but Gröbner basis need not have, because I could have added a few more terms here and then try to find Gröbner basis. The outcome would have been different. Okay.
Thank you.
Yeah. Let me just share my screen again. Okay, so I hope this is visible now. And let me move to next question. Let R is equal to K x1 to xn. So K is polynomial field. And this M is ideal generated by these variables. Okay. and F1 to Fm are elements from this M square. Okay, so now this M square is what? M into M. So it is ideal generated by F into G such that F comma G in F. Okay, so this is my M square, and I is this element ideal generated by this F1 to Fm. And now they are considering G be a Gröbner basis of I with respect to the graded reverse lexicographic order, or what we call it as degree reverse lexicographic order. Then we have to check whether true or false, and the statement is for each G in G, this G is Gröbner basis, degree of this initial term of G is greater than 2, or degree of initial term is actually equal to degree of G anyways, so doesn't matter. So they are saying that this degree of G is greater than equal to 2 or not. So G is, so we started with the polynomial ring. This M is ideal generated by all the variables, and we are choosing some polynomials from this M square. Okay, so for example, if I take just an example, if I take this x1 to xn, then this is my M. So M square is what? It is ideal generated by these terms. Okay, let me just write. This is like x1 square, x1, x2, so on up to x1, xn, then x2 square, x2, x3,
It's
so on
basically
up
any
to.
permutation of the n.
Yes, all the two permutations or all the two choices of variables. Okay, and x3 square and so on. And the last term will be xn square. Okay, so it is this. And when I take this f1 or this fi, it could be anything. It is a polynomial in this ideal. Okay, so it could be very well x1 square plus x2 power 4 plus x2, x3, 7, or here let me write x5 power 100. Doesn't matter. It is just any polynomial from this ideal M. So this, let us just write some fi is this. So this polynomials. So they are saying we are choosing such M polynomials. And now we are taking taking Gröbner basis of this ideal generated by. So I is F1 to Fm, where this FIs are in M square. Okay, and G is Gröbner basis of I. And we have to check whether when we have Gröbner basis of this ideal I, its degree, the degree of each term is greater than equal to 2. That's true or not? Yes, it is true. Yes, as Rishad said, it is true. The reason being, note that this all F1 to Fm are belongs to I, but I is anyway contained in this M square, right? And this M square is monomial ideal. Okay, and anything belongs to monomial ideal if and only if each term of that. So we have this result that let I be a monomial ideal of R, then F belongs to I if every term of F belongs to I. This is true only for monomial ideals. Okay. So in that case, when I say some thing belongs to. So when I say that G belongs to G, this implies that G belongs to this I square as well. Sorry, I as well, right? And but this I is anyway contained in M square. So each term of G is divisible by is an element of M square. Okay. I mean, I hope you all are following the argument. If there is any doubt or any error, please let me know. Each term of G is an element of M square, and M square is generated by all 2-degree elements. If something belongs to M square, one of those monomial must divide that polynomial that term, right? So these imply that degree of G must be greater than equal to 2, because every term degree of, let me write, term G is greater than equal to 2, or this is very bad way. Degree of U is greater than equal to 2 for all U belongs to, I'm just creating set of terms of G. Okay, since G belongs to M square. And since each term has degree greater than equal to 2, the largest possible degree will be, when I take maximum over those terms, maximum of the degrees of those terms, it will definitely be greater than equal to 2. So the initial of G must be greater than equal to 2. Degree of initial term of G is greater than equal to 2. Therefore, degree of this G is greater than equal to 2. Is this okay? Any where you are unable to follow? Okay, clear. Everyone else, like, okay. If there are doubts, please let me know. Okay, so if it's clear, next question. Just a second. Now, question 4. We have to find the cardinality of a minimal generating set of the ideal x square y. Let me just write small. x square y, x z square and x square z. Okay, of the ring K x y z is. So they're asking us the cardinality of minimal generating set. So minimal generating set is just a generating set with the minimal cardinality, and D is none of the above. Okay, so we have this generating set x square y, x z square, x y, x square z. Any guesses? What will be the generating set? Okay, your guess is 2 is the minimal generating. So it must have 2. So which 2 elements are your guess? This one and this one, or these 2? Okay. Now, so Rishad guessed 2 and Vijay guessed 3. So note that.
No, x square y and x square z, that would be generated by x square. So those two I can
so we,
remove. So it should be less than equal to 3. So
yeah,
I'm wondering, like, I can't remove anyone else.
yes, exactly. That's true. So this two we can get rid of since x belong to, sorry, x square divides x square y, and this or this is what? This is just x square into y, and this is x square into z. So we can get rid of this from the minimal generating set. But these three, x square, xz square, and xy, none of them divide other, or none of them can be written as multiple of other. Okay, so okay, x square needs to be there. X square helps us to get off those two terms, but x square has to be there in the generating set. If you like removed all the terms which were multiple of x square, then that's not the case. Okay, so these three are, so guess is that this mu of I is 3. This is the symbol which we use to write the cardinality of minimal generating set of I. Okay. And Macaulay 2 also has some functions which we can use to find a minimal generating set. So let me just define this ideal. Okay, so we anyway are in 3 variables. So let me just write this. Clear everything. Okay, and now let us define x, y, and z. And now I is ideal. X square, x square, y, x, z square, x, y, and x square, z, x square. I hope this is the correct idea. X square, and this. Okay. But when I give this command, numgens of I, oops, sorry, typo. Numgens of I, it says 5. It is just giving me the number of generators the way we defined the ideal. Okay, if I had added one more monomial here, it would have said 6. Okay, now we have to get rid of so something called as this. To get the minimal generating set, we have this command, mingens of I. Now it has only these 3 elements. These were the exactly 3 elements which we were also getting. So this is so this 3 here is the cardinality of this minimal generating set. And the another way to get it in the ideal form is trim I. So trim I actually gives me an ideal which is minimally generated from I. So it is equal to, so trim I is equal to I. This is always the case. But when I say trim I, so numgens, when I write numgens of trim I, it gives me 3. So it now considers it as ideal generated by 3. It is actually I, but generated by 3 elements. When I write I and gives command numgens, it gives me 5 as answer because I defined this ideal I with 5 generators. Okay, and that's it for now. I mean, the numgens, and yeah, and one more thing. When we do this numgens, is ideal generated by this numgens of I is equal to this trim I. Okay, because they are exactly the same ideals if you see. Is there any doubt now? So that's how we can see how. So if you have any ideal, if you want to calculate its minimal generating set, it gives us the generating set, and numbers give us the number of generators which we used when we defined that ideal I, and trim I just consider I as the element ideal generated by the minimal generators. Is it okay? I hope this is okay. These are just some functions which are there in Macaulay 2 to check the minimal generators and number of generators. And you can use this to find the required information which you need. Okay. So that's it for that question. Any doubts in that question? Please let me know. Otherwise, I will move to now the next question. This is my eye.
Ma'am,
Yes.
thus every ideal has a Gröbner basis, right? Reduced Gröbner.
Sorry.
It's not
Hello.
in every Noetherian ring, every ideal has a Gröbner basis, right?
You are saying in every Noetherian ring, every ideal has a Gröbner basis, right?
Yes.
Yes, it's true.
So if I fix an order, then minimal things at that side, that the cardinality of that side unique, right? The cardinality
Yes.
of
Yes.
this is exactly same as the Gröbner basis.
No.
Reduced.
No, when in the reduced case, it will never be equal. Not never. There are cases where it's not equal.
So
The
is it
Gröbner
unique
basis,
for any ideal? Like
what the
for
minimal
any ideal?
generating?
Yes.
Minimal generating set. I mean, it again depends on what you are choosing to generate that ideal. Yes, but minimal generating set, yes, this is unique. This is unique.
But now
Whatever
I'm not giving the generating set. I'm just giving any ideal in Euclidean ring. And you said there is a Gröbner basis for any ideal.
Yes.
So now fixing that order, I have a generating set, but generating set may be different, may have different generating sets. So the minimal, I want to associate some the cardinality of minimal generating set for an ideal without giving the generating
That's why, yes. Minimal generating set, the cardinality of minimal generating set is always, it is independent of order. The cardinality of minimal generating set is always independent of order, because it is like minimum of cardinality of G such that G is generator of I, right? This will be unique because, and this is what is my MOI is. So cardinality of minimal generating set is always unique. Is it okay? Hello?
Could you elaborate, please?
Okay, so the mu I is actually cardinality of minimal generating set. So when you talk about minimal generating set, you don't start with any generating set. You know the ideal, you know the elements of those ideal, and you try to find a set with minimal cardinality which generates that ideal. Okay, so in earlier case, when we saw the example where Gröbner basis with respect to graded reverse lexicographic order has 4 elements. lexicographic had 10 elements, but the minimal generating set of that ideal had 3 elements. Okay, and the the cardinality of minimal generating set is always fixed. This mu I is well defined, but way you want to choose the generators depends. For example, if you take Z is a ring and you take this ideal 1, okay, and also ideal generated by 2 and 3. So these two are same ideal, but this is minimal generating. Minimal generating. This is also minimal generating, right? For us, this is commutative with identity. That's not a problem. So when you talk about minimal generating set, it is different. But when you say this, when you write this, it is 1, it is not 2. Because we are now, when we define this, we are taking minimal over all the generating set. Now, is this okay?
Yes, thank you.
Okay.
Yes.
Okay, so the difference between the cardinality of minimal generating set, that is this mu I, is unique, it is fixed. But the minimal generating is something different. Okay. I hope this is okay. And yes. If there are still any doubts, please let me know. Or I will move to the next question. We have time. Yeah. Is there any code in Macaulay to find? Yes, that min gens, if you do, it will give you the minimal generating set of I and num gens of trim I. This, let me just write it in green. Macaulay to this num gens trim ideal I or just I. This I is ideal. Okay. This you can do. Okay. And this will give you mu of I. Or when you find this min gens of some ideal I, Macaulay 2 gives you it in the form of matrix. And it is 1 cross n matrix. And this n is also our mu I. So there are multiple ways to look at it. As far as I know, there is no direct, I don't remember right now, code to find number of minimal generator, but this works for now. If I find any other function, I will definitely let you know in the next lecture, or I will add it in the notes in this PDF. But you can use these two terms, at least these two methods, and this just to find your generators or number of minimal generators. Okay, so let us move to now next question. I hope there are no further doubts. If there are doubts, please let me know. Otherwise, we will move. Okay, just a second. Question 5 now. Again, we have to check true or false. And now we are in CXY. So we are in polynomial ring over complex variables. And the idea x plus 1, y and z. This is my I. We have to check whether it contains the ideal J, which is defined like this: Z, comma, YZ, 2y square plus y, comma, 2y square plus y, comma, xy minus y, 2xy plus x. So this is the question. So they are asking us whether ideal I contains J or not. So that is, in short, we have to check whether J is contained in I or not. And what is your guess? So how to check whether this J is contained in I or not? See, we are given this list of polynomials which is J. So if each of this element is in I, then this J is completely an I. Let me just write this. If every generator, generator of J, let me write here, given generator of J is in I, then clearly J is contained in I. False, can you?
I
Yes,
don't.
which?
I think it's false because like 2xy plus x.
Mhm.
I don't think that can be generated.
Okay, so he definitely that element. So his guess is that this element does not belongs to I. Okay, so clearly this Z is in I, YZ multiple of Z is in I. This is just something generated by Y, that's why it's there. And this xy minus y is, how can we write this? Can we write this?
No, I don't think.
Okay, let us see. Xy minus y. So it is x into, so we have x plus 1, right? If I do this, what is this? This is xy plus y. And now we have minus y. So if I do this, yeah, so this is there, right? Someone wrote? Yeah. Yes. Subhadeep, yeah, the argument for 2x plus is correct. Okay. So this element at least in I, because it is x plus 1 into y minus 2y. So this is in I. But yeah, this 2x plus y, sorry, what is it? 2xy plus y. Yeah, understood. 2xy plus x. How can we write it as? It is 2x into y, because we have y there in I, and x plus 1 and minus 1. Okay, so this and this two are there. So if I consider this, if 2xy plus x belongs to I, then this 2xy, 2x plus x minus this 2xy plus x plus y belongs to I, because belongs to I. So this implies that minus 1 belongs to I, but which is not true, right? So as we can directly say from here, these two terms are there in I, but this final term doesn't belongs to I. Okay, so
Like how can we say it is not a proper ideal?
it's not proper ideal. It's not at all contained in I. It's not contained in I. This
Is it given ideal is proper?
proper. Okay, so you're saying that
Why one is
it
not
is.
there?
So I given, right? I is this. I is this. X plus 1. Sorry, x plus 1 or minus 1? X plus 1, y and z. And yeah, as you said about the proper, if you remember, we have this result from that if K be any field, and R is K x1 to xn, and let A1 to AN double in this field, then the ideal x1 minus A1 xn minus AN is maximal ideal. Yes, yes. Okay. So what Shubhadeep said is also correct. And also we have this remark, which is easy to follow. So I can write this ideal as x minus minus 1, y minus 0, z minus 0. So this ideal I is maximal by following remark. Now is it clear? Therefore,
Yes.
okay. Therefore, 1 doesn't belongs to I, since I is maximal. Okay, so that's why this minus 1 does not belongs to I. Now it's clear, therefore this is false. J is not contained in I. So this is false. Okay. Any doubts here? And to check the containment of ideal also, there is code in Macaulay too. We'll check that also quickly. I will just show you. I am not writing this entire. Let me just take any two ideals. So I'm taking this ideal x1, comma x2. Oh, x or z, since we are. So my polynomial ring is x with variables x, y, z here. So let me take that. Is x comma y. And let me take j to be ideal. This is just to show you the code for it. And let us take just ideal x. Then you have to write this subset. So you have to check whether j is a subset of I. So is j a subset of I? Read it like this. Is j a subset of I? So that you don't forget the order. Then it's true. Okay. If you change the order, it differs. Okay. I is not subset of j, but j is subset of I. Or let us just quickly check our ideal as well. Our ideal I was this x plus 1, y, and z. And j was this ideal. Z, y star z, 2 y square plus y, 2. Let us see how it takes 2 into you need to write here. Okay. It 2x star y plus x comma x star y y y. Let us check. Okay. And is j a subset of I? And it's false. Okay. So you can use this function of Macaulay to check whether and this is not only for ideal, this is for any subset. Okay, so you can just define any set in Macaulay 2 and check this. So this is not specific to ideal. You can just generate a list in Macaulay 2 and check whether one list is in other or not. So this function is true for any subset. Okay, and not only for ideals. Okay, is this okay? This function? And I guess that's okay. Let me go back to, if there are doubts, please let me know. Otherwise, we will move to next question. Okay, Now this is question 6. Again, we have to check true or false. First, they are saying a Gröbner basis for the ideal I is equal to z plus 1, yz, 2y square plus y, 2xy plus x, xy minus y plus 2 of. This is now real. The G Reiblich. So this is a degree reverse lexicographic order. I'm writing it as G Reiblich. Contain 1. Okay. So we have to check whether 1 belongs to the Gröbner basis of this ideal I or not. Any guesses whether 1 belongs to this ideal? See if it belongs to. So 1 belongs to Gröbner basis means 1 is also a element of that ideal, right? Because Gröbner basis is a generating set of that ideal I. So if 1 belongs to some generating set, then that 1 needs to be an element of that ideal I. Okay. So what is your guess whether 1 belong to that ideal? A quick Gröbner basis of, so G is a, let me just again quickly define what is of I. You can think of it. I am just writing this if initial terms of G such that G in G. Okay. And this is this ideal generated by in F, F in I. These two are different sets, okay? And of course, this cardinality and if. Okay. Any cases whether 1 is there or not? So to check whether 1 belongs to G, that is, let me write GB of I. We need to show that we need to check that whether 1 belongs to I or not, right? Because anyway, 1 is less than equal to
If
M.
we can manage to show that some like x is not there or y is not there, then we are through.
Some polynomial, you are producing a polynomial which is not there, because then 1 will not be there, because if 1 is there, it will be whole ring. That kind of stuff you are trying to do?
Yeah, yes.
Okay. So can you produce such element?
I'm guessing if we can try for x or something. I'm not sure.
This is 2, by the way, okay? This is 2. Can we do x? I don't know about x, but I know how to do for 1. So let me show you that for all monomials. Okay, so or x also we can do. Okay, so x is xz into minus y plus 2. So this last element plus x square plus 1 into yz plus 2x into z plus 1. Oh, here it will be x. So it will be what? X square yz plus xyz minus plus, this was minus, plus 2xz plus x square yz should be minus, I guess, here. X square yz minus xyz. Am I? Let me just do something. And plus
Can you
2x.
just show the
Yeah.
question again?
Sorry?
Can you just show the question again?
Yeah. We have to check whether one belongs to the Gröbner basis of this element or not. And one is smaller than any polynomial. So any monomial. For any given polynomial, its initial term will always be greater than equal to 1. So to order to
Like,
see this,
The
we are,
like, one is a constant polynomial and
yes,
z plus 1 is a linear polynomial. Right?
yes.
So is there a way that we can get 1 from this z plus 1? Because every other polynomial is of higher degree.
Yes, we can.
But working with z plus 1 is most useful.
Yes, we are working here with plus 1.
Okay.
Okay. And here we have minus 2x. So if I'm just writing here x because you asked about x. But yeah, so when I do this, this is minus 2x. And let us see. This gets minus plus, please help me adjust minus plus. Here it is minus plus, yeah, it's correct. And then this xyz, this xyz gets cancelled, and this xz and or let me just box this. This gets cancelled here. I have to adjust the minus. Here it must, so here plus, here plus. So I have 2x here, and when I multiply it by 1 by 2, this entire term, I get this x which you needed. And in general, to see how one looks like, it is this. It is z into, let me just write z like this for now to avoid confusion, minus x plus 1 into yz. It was x plus 1, right? Okay, x plus 1 is what I need, plus 2z plus 1. Okay, and it is 1 by 2, 2, and it is 1, which belongs to I. Okay, so it is ideal generated by 1. So 1 actually belongs here. You have to do calculation. So actually 2 directly belongs there, but we are in R, so we can multiply it by 1 by 2 and we get back 1 in I. Is it okay? You can see this. This is xyz. Here xyz gets cancelled. Here xz. Here. This zy gets cancelled with this zy. This 2z gets cancelled with this z, and we are left with this 2 here. Okay, and when I multiply it by half, I get this 1. Is this okay? The calculation. So as you said, we actually needed this z plus 1 to obtain this one. Okay, so we somehow use this, not these two polynomials, this one and yz. So here we have z, here yz, and here y, and we got that one belongs there. Okay, any doubts here? But in this ideal, I am trying to compute mean gens in Macaulay 2, but is showing over inexact field, begun result not reliable one. Okay, so you are working with R, right? So Macaulay 2 is of course yes. So when you do R also has irrational numbers like pi, e, and so on. So those are like not fully defined in any PC, right? If you know, it works fine with rational fields, but when it comes to R, because of irrational numbers, it will give some error. Okay, yeah, I know you got it. Because of the irrational numbers, it shows that warning. Because if pi, sorry, for example, your ideal actually contains x minus pi on paper, but Macaulay 2 doesn't know all the digits of pi. So it will give you some ideal which is like different from what you actually want in R. So that's why when I show the calculations here, I mostly do it over rational fields to uh, avoid such warnings. But we did not have such problem because all the coefficients were inverse, in fact. So that's okay. But I hope you got this, that this ideal actually contains 1, and that's why it will also contain in the Gröbner basis. Okay, so let us try to find Gröbner basis of this and mean gens of this to see how Macaulay 2 gives the outcome. Let me share screen again. Okay, let me clear everything to avoid confusion. And it was graded reverse lexicographic order, right? So R is a ring. Yes, but thinking the coefficients are problematic. No, I could not get what you are trying to say when you wrote this last line. Could you please? Okay, okay. Let us do that. Okay. Yes, yes, that's true. I mean, calculations are not as easy, or it's not easy to follow always. So yes, y square plus y. Let me just y plus x star y minus y plus 2. Okay, so I is this ideal, and this is the code, as I already said. It shows Gröbner basis contains only 1. Okay, because Macaulay 2, when I ask for Gröbner basis, it gives me reduced Gröbner basis. Okay, and let us see what it gives me when I say mean gens of I. It gives me these 3. 1, z plus 1, y and x. But when I do trim I, it just shows me this. Yes, I mean, you can also do this. Ideal, okay. Whether I is equal to ideal generated by 1, I guess I gave polynomial ring R, okay? And it's true. Okay, ideal generated by I is equal to this ideal generated by 1R. So it is entire ring, in fact. Okay, and its subset is also work as Subhadeep suggested. And yeah, so there are many things. So you can define such ideals and check what Macaulay 2 does with this. And to check, so if you gone through that non-graded assignment sheet, it has given us, it has many Macaulay 2 codes written there. Okay, please go.
I don't understand the O34A here.
Yeah, yeah.
That one is there. Why one? If one is there, then the XY is there.
Because I think it's because we defined the ideal like this. Even when I calculated this, it showed this, but when I do trim, it shows only one. So this is strange. I don't know why. So there is something called as this code mingens. I guess you have to do something like this. Ideal. I don't know. Okay. It's given in the sheet, an assignment sheet, and you can check what actually mingens do when you try to calculate mingens in Macaulay 2. Okay, and you can check like what is the algorithm which Macaulay 2 uses to find this minimal generating set of ideal I, and that will help you to see why this is giving this as a minimal generating set and why this trim I. At the end of the day, I mean, this is just a software which runs on some functions which are defined, and it's just the way we have this here. But it should have ideally said just one instead of having showed it like this. Is this okay for now? And yeah, this is something I wanted to show that yeah, whether x divided by I, what this shows, it shows 0. So it's like when I check whether this x is in element x is in ideal I or not, it shows me 0. Okay, and in general you can also do this x divided by. So this is not divided by, this is actually reminder when x is divided by I. So when I do this, that whether x is what I do is I take x, I divide by x by every element from the generators of I, and check what is my remainder. That's how we get it. And James GBI, or it also works with just GBI. I'm just showing you multiple ways. Okay, so this will give me reminder, or if I just define some ideal like this, x plus 1. Now this is maximal ideal, okay? And when I do this xj, and it shows me -1. Okay, so you can find the remainder, and also let me just write x plus y square minus z, and it will still, because it's the -1 which is playing, and everything in the y and z terms are there in this polynomial. Okay, so you can do this to find the remainder, and so on. So I hope this is okay. I will also again go through this mingens as pointed by Rishabh, and see why we are getting this. And meanwhile, if you find any answer, please feel free to write it in the discussion forum. Okay. So for now, I guess this is okay. We will move to next question. If there are doubts, please let me know. And otherwise, we'll move to next question if we have time. So this is true, okay? Gröbner basis actually contains 1. Any doubts here? Please let me know. Okay, no. So let us again, this is again true or false question. And we have this ideal, the ideal, z plus 1. So this is z. Let me write it. Yz 2y square plus y 2xy plus x comma xy minus y is a maximal ideal of this q x y z. This is the question. We are asked whether this ideal is maximal or not. Any cases?
The same idea. Same idea.
It's actually not the same. Here we had 2. Here we do not have that 2. So it's not same. Yeah, the first few terms are same from the earlier ideal, but it's not exactly. So more or less, apart from this 1 here, everything is same, right? Apart from this 2 here. So can we obtain something? So note that we are in the field. So let me just write this. Let K be any field. Then R is equal to K x1 to xn. And I'm just repeating what I wrote earlier. It's some n tuple. Then the ideal x1 minus a1, x2 minus a2, and so on, xn minus an is maximal ideal. Okay, and if you know that this x1, x2, an, this a1, a2, an actually gives is what I can say, 0 of these polynomials. Okay, so here if I want to express this in this form, so we just have to find like what these a1, a2, ai's must be. Okay, so for example here z is equal to -1 means yes, minimal generating set is x, y, z plus 1. So you tried it using so you did it by hand or you did it using Macaulay too, that it is minimal generating set? Okay, by hand. Could you please tell me what are the generators of x, y, z? So z plus 1 is there, that's not a problem. Okay, how can we write x? X, okay, so x can be written as yes. So y is y into z plus 1 minus yz. Okay, using these two terms, z plus 1 and yz. And xy is, yes, xy, x is x into 2y plus 1 minus 2x into y. So how I got this 2y plus 1 is, so the moment I have y, I can get rid of terms which contains y. Okay, so y is a monomial, so I can just remove all the monomials which has y. So this is gone. Okay, this is gone. Now I have this. Okay, I have y in this ideal, so I can just do this since so y belongs to I, so therefore 2xy plus x. So x will be this 2 into xy plus x minus this 2x into y. Okay, yeah, that's what even, since now y belongs to my ideal I. So therefore, x belongs to I, y belongs to I, and z plus 1 belongs to I. And by above remark, it is of the form x minus 0, y minus 0, z minus minus 1 is I, is this ideal. And this is maximal ideal in R. Is this okay? Or maximal ideal in Q, X, Y, Z. Any doubts here? Okay, then you can do it by hand, or you can also try to use Macaulay to obtain this minimal generating sets and so on. Any doubts?
Clear.
Okay, clear. Great. So we will move to now next question. Okay, and when you are using Macaulay to solve your assignment question, use it. No, I mean, that's not a problem. But also when you see the answer, please try to do it by hand. Okay, I mean, by using proper calculations and so on. So they're saying that what is the number of points in the variety of the ideal x cube plus 1 in the ring Cx. So we are in now polynomial ring in single variable in over complex coefficients. Okay. So definition of variety, let me just recall it. So K be a field and R be this polynomial ring x1 to xn. Then a subset Z in K power n. So Z is contained in this K power n. Okay, so it is kind of tuple, is a variety. In our case, since we only have one variable, it will be just a point. I mean, it will be just one element or tuple with, I mean, tuple of this sort. I mean, I hope you understand what I'm trying to say here. Variety of a variety, if I is contained in R, there exists ideal I in R such that Z is equal to Vi is equal to A bar. So A bar to denote that it is a vector and not just element in K. And just that f of A is 0 for all f in I. Yes, it is 3 because C is anyway algebraically closed field and we have a polynomial here. And but again, they are asking about the points in variety. So we have to check respect to multiplicities. So 1 is surely there. Okay, minus 1 is there. So variety is in short 0 set of element which is 0 of all the polynomials in that ideal. And note that since we are working with the ideal, it is enough to check the element in variety over the generator. So if something makes something is a root of all the generating polynomials, then it will be a root for all the polynomials in that ideal. Okay, so C is algebraically closed field. So therefore, there are definitely 3 points counted with multiplicity. Okay. So now so this is what? X cube minus 1. So this is x cube minus 1 cube. So we have this a cube minus b cube formula. A cube a square plus ab plus b square. Okay, we will just use that. It is, I mean, we can also divide this polynomial and obtain this, but since we know this, I will be just using this. This is x minus 1 cube x square plus x plus 1. Okay, so one root is minus 1. Oh, sorry, one root is plus 1 because it is what? Am I missing something? Okay, so ideal is generated by plus 1. So this is this. Sorry. Plus 1 is x minus minus 1 and this. So this is x plus 1. And this is quadratic polynomial in 2 degree, and we will just use that discriminant formula, and we will get that minus b plus minus roots b square minus 4ac by 2a. And when we do that, it is x minus minus 1 plus root b square is 4 minus, so it is 3 by 2, and it is 1 minus root minus 3 by 2, and it is just this x plus 1 x minus minus 1 plus, we are in complex, so that's not a problem. This minus under root is not a problem.
3.
Yes, is there any problem?
It's going to be root 3i, not 3a.
Okay, it won't be
Like,
b squared 1 minus 4, right?
yeah, so it's like in the last step, it should be root 3i, not 3a.
This one?
No, the step below this.
Mm-hmm.
It should be minus 1 plus root 3i by 2, not 3i by 2.
Minus 1? Oh,
Plus
root 3i. Oh,
below
okay,
that.
okay. Got it. Sorry. Minus 1 plus, plus root 3i by 2, and okay. Thank you. Root 3i by 2. Okay. So these are two distinct points. Please see whether this minus and everything is okay. So therefore, there are 3 points in the variety. Okay. Any doubts here? And I checked, but there are no, I mean, I could not find any function which will give me 0 of a polynomial in Macaulay 2. So if I find, I will definitely let you know. But for now, whatever this was, you have to just calculate it by hand. Okay. If there are no doubts, I will move to next question. Okay. We'll just do this question quickly. It's already 5, but let's see. The number of points in the variety. Again, it is more or less the same question, but now you will see what's the difference. In the ring Kx, so it is again filled, oops, not here, filled in one variable, where this K is a field of characteristic 3. So that is the difference. Earlier we were working over complex. Now we are doing it over a field of characteristic 3. So here K, a field of characteristic 3 is just Z3. Okay, it will be isomorphic to Z3. All the fields of characteristic 3 are 3. I mean, it is this field Z3. Okay, so we have to check Yes. Cardinality is 1. The number of point in this variety is just 1, and we will check which one is it. So we have this Z3 means what? We have this 0 bar, 1 bar, and 2 bar. And we will check just 3 are there. So we will substitute them. Plus 1 bar. It is 0 bar plus 1 bar, which is 1 bar, which is not equal to 0 bar. Second
Only
one
X plus
is,
one.
yes.
Only X plus 1 will be.
Yes, I mean cube is again in Z3, it's cube plus 1, which is 1 cube, 1 plus 1 bar, which is 2 bar, which is again not equal to 0 bar. And again 2 bar cube plus 1 bar, it is equal to minus 1 bar cube plus 1 bar. It's equal to, and finally we get this 0 bar, or this, if you want to write, this is 8 bar plus 1 bar, again 9 bar, which is 0 bar. Okay, doesn't matter. So variety of this ideal x cube plus 1 variety over F3. Okay, field of characteristic 3 is just 2 bar, and therefore its cardinality is 1. Any doubts here? I mean, this was easy because we just had to check 3 elements. Any doubts here? I don't think you will be having any doubts here. It was quite easy. But apart from that, any doubt in the intersection, it is already 5-4. So, I mean, if there are no doubts, and also like there is extra section of problem solving session is added in the portal. So please go through it. And so last time, since that section was not there, you could not access the PDFs and everything the same day. But from today onwards, you will be having the recording of this video lecture and all the notes and everything by end of the day. Okay, any doubts further? Doubts about anything related to the course, or any definition or anything? Macaulay 2 course which you could not solve last week. Was that okay?
Yeah, it was okay. Yeah.
Okay, and also there was this, I added slides at the end of the PDF last week. Please go through those. I mean, try to do those calculation by yourself in Macaulay 2, so that it will become handy. I will also add the code for today's lecture in Macaulay 2 as much as possible, and we'll see. And please feel free to write or try to, I mean, feel free to post your questions in discussion forum. Okay, if there are no doubts, I guess we can close the session, or you can ask me any doubts if you want for now. Okay, okay. Great. Okay. If no doubts, then I guess we can end the session for now. And if there are any doubts, please let me know. And feel free to ask questions in discussion forum, and you will get all the information about today's interaction session in problem solving session section in the portal. And we'll meet next week same time. Okay. Thank you.
Thank you.
Yeah.